Welcome to this explainer. Look, if you've got a thermodynamics exam looming on the horizon, you are absolutely in the right place. Today, we're taking a deep dive into the fundamental rules that govern energy, engines, and honestly, the entire universe. We're talking about the science of heat, work, and temperature. By the end of this prep session, you're going to understand the absolute limits of physical reality, and more importantly, you'll be completely ready to ace those tricky test questions.
All right, here's our study roadmap for today. First, redefining heat and energy. Second, the anatomy of a system. Third, the first law. Fourth, mapping thermodynamic processes. And finally, number 5, entropy and universal limits. Let's jump right in.
Section 1, redefining heat and energy. For a really long time, the scientific consensus was this totally outdated concept called the caloric theory. It was this wild idea that heat was a literal, invisible fluid just flowing between bodies. But for your conceptual exam questions, you've got to remember the year 1798. That's when Benjamin Thompson, also known as Count Rumford, completely shattered this idea with his cannon boring experiment. He literally used horses to drive a blunt drill into a brass cannon barrel submerged in water. The friction generated so much heat that the water actually boiled without a single spark of fire. This brilliantly proved that heat isn't a fluid at all. It's a form of energy in transit, generated by work.
So, this huge paradigm shift sets up a classic trick question you're almost guaranteed to see on multiple choice exams. Knowing the difference between what a system inherently is and what it does. On one hand, we have state variables, which define the current condition of the energy a system literally possesses right now. On the other hand, we have transit modes. These are simply the active methods by which energy is currently moving in and out of that system. Keep those completely separate in your head.
Picture this. Inside a cylinder, you've got gas molecules just buzzing around chaotically. The total sum of all their kinetic and potential energies, that is your internal energy, or U. It's a classic state variable. But notice how the energy actually flows here. Work, or W, is transferred mechanically, like a physical piston compressing the gas. Heat, or Q, is transferred via temperature difference, like sticking a hot flame at the bottom. The key takeaway, a gas never intrinsically has heat or work packed inside it. Heat and work are strictly modes of transfer that end up altering that internal energy.
Section 2, anatomy of a system. Okay, here is a quick mnemonic that is going to save you on test day. Listen to this. Intensive variables are independent of system size. Notice the N? Intensive, independent. If you cut a box of gas perfectly in half, the pressure and temperature inside those halves remain exactly identical. Extensive variables, however, depend entirely on scale. So if you cut that same box in half, the total volume, mass, and internal energy are literally sliced right in half along with it.
Which brings us to the equation of state. You'll definitely want to circle this formula in your notes. PV equals mu RT. For an ideal gas, these macroscopic variables aren't just random numbers floating around. They are strictly mathematically linked by this equation. Think of it like a giant puzzle. If you know the pressure, the volume, and the amount of gas, boom, you automatically know the temperature. You literally cannot change one without forcing a shift in the others just to maintain that mathematical balance.
But how do we actually physically define temperature in the first place? Well, that is exactly what the Zeroth law of thermodynamics is for. It establishes thermal equilibrium. Imagine step 1. Systems A and B are totally separated by an adiabatic wall, meaning absolutely no heat can flow between them. But they are both connected to a third system, C, via a diathermic wall that does let heat flow. If system A synchronizes its energy state with C, and B also synchronizes with C, then step 2 gives us an undeniable logical verdict. A and B must also be in perfect equilibrium with each other. And that equalizing physical quantity, we call that temperature.
Section 3, the first law.
All right, the first law of thermodynamics. This is the absolute bedrock principle of cosmic accounting, and it is a guaranteed problem type on your exam. Delta Q equals delta U plus delta W. It's simple. Energy cannot be created or destroyed. If you supply heat into a system, like that large red arrow you see right there, that energy has to mathematically split. It can either raise the internal energy, U, which means more microscopic molecular jiggling, or the system can use it to do actual physical work, W, by pushing a piston outward. Every single joule has to be completely accounted for.
Now, when you're sitting there trying to break down complex word problems, keep this crucial shortcut in your back pocket to save time. While the exact amounts of heat and work depend entirely on the specific, messy path you take from state A to state B, the overall change in internal energy does not. Whether you pump in a ton of heat and do very little work or vice versa, the net difference in your internal energy is completely path independent. It only cares about exactly where you started and exactly where you ended up.
Section 4. Mapping thermodynamic processes. Before you even attempt calculating process maps, you have to understand the major difference between messy reality and our neat physics models. Take reality, like free expansion. Gas bursting out into a vacuum is completely chaotic, with totally undefined pressures and temperatures. You can't calculate that easily, so to actually solve exam problems, we rely heavily on the ideal scenario, the quasi-static process. We pretend that changes happen infinitely slowly, so the system basically stays in perfect thermal and mechanical equilibrium at every single microstage. It's a hypothetical construct, but it's what makes all the math work.
Honestly, take a screenshot of this matrix right now. It is your ultimate visual cheat sheet for the exam. By using that quasi-static ideal we just talked about, we can perfectly map 4 constraints. Let's do a quick practice quiz right here. If we hold temperature constant, that's isothermal, internal energy stays completely flat, so every bit of heat converts directly to work. What if we fully insulate the system? That's adiabatic. 0 heat flows, so any work done drops the temperature. Lock down the volume? That's isochoric. The system literally can't move, so 0 work is possible, meaning heat goes straight into internal energy. And finally, lock the pressure for an isobaric process where heat splits perfectly into both work and internal energy. And you will almost certainly be asked to identify these specific PV curves on your test. The isothermal curve is that gentle, sweeping slope you see. The adiabatic curve dives way steeper because expanding without any heat causes a rapid, massive pressure loss. The isochoric process is probably the easiest one to spot, just a straight vertical line where the volume mathematically cannot budge. And the isobaric process, just a perfectly flat horizontal line representing constant pressure.
Section 5. Entropy and universal limits.
Enter the second law of thermodynamics. This introduces a pretty brutal physical reality, irreversibility. Spontaneous, natural processes only ever go one way. Think about friction heating up a car's brakes. You can never just spontaneously run that clock backward. This gives us what we call the twin statements, which are prime targets for true or false and multiple choice questions. The Kelvin-Planck statement firmly dictates that a perfectly efficient engine is impossible. There is no way you can convert 100% of heat into work without creating waste. And the Clausius statement tells us a perfect refrigerator is impossible. Heat is never ever going to naturally flow from a cold spot to a hot spot without you putting in external effort.
Let's see how this builds into the ultimate theoretical limit, the Carnot cycle. French physicist Sadi Carnot brilliantly designed a totally hypothetical engine that navigates these strict laws of physics with maximum possible efficiency. You definitely need to memorize these 4 distinct steps for the exam. Step 1 is isothermal expansion, where heat slowly enters at a high temperature. Step 2 is adiabatic expansion, where the newly insulated gas does work and begins to cool. Step 3 is isothermal compression, where it dumps its waste heat into a cold sink. And step 4 is adiabatic compression, insulating the gas once again and forcefully compressing it right back to the start.
If you chart the Carnot cycle on a PV diagram, it is beautifully constructed from 2 gentle isothermal curves cleanly connected by 2 incredibly steep adiabatic curves. It is literally the only perfectly reversible cycle imaginable. It absorbs heat, does actual work, and dumps waste heat without ever introducing a finite temperature difference. That means absolutely 0 friction, 0 turbulence, and 0 wasted mixing. It is absolute theoretical perfection.
And because it is completely perfect, it gives us Carnot's theorem, the absolute universal ceiling for efficiency. Check out this golden equation. It tells us that efficiency equals 1 minus the temperature of the cold reservoir divided by the temperature of the hot reservoir. This is incredibly profound for your test calculations. It means that maximum possible efficiency has absolutely nothing to do with what your engine is actually made of. It depends solely on the temperatures of the hot and cold reservoirs. And since no cold reservoir in the universe can ever reach absolute 0, achieving an efficiency of 100% is physically completely impossible.
So, to sum up this whole study session, these are the 3 giant pillars of macroscopic reality. The Zeroth law, establishing equilibrium and temperature; the first law, locking down the conservation of energy and work; and the second law, enforcing entropy and irreversible limits. For your actual study schedule in this final week before the test, I highly recommend reviewing exactly one of these pillars per day. Break it down, and it'll help keep the concepts completely distinct in your mind.
Which leaves us with something pretty deep to ponder. We've seen today that the math of energy transfer is incredibly tight and unyielding. But if every single spontaneous natural process is fundamentally irreversible, it begs a massive question. Can the cosmic clock ever truly be run backward? Or is the relentless forward march of time just the ultimate inescapable consequence of thermodynamics? Thank you so much for joining me on this explainer, and best of luck on your exam. You're going to crush it.